Well, my student, today I shall talk about method of partial analysis. It's a technique of analyzing the scattering phenomena. In our last class, we all have learned about the development of general scattering theory. But today, under that same framework of scattering theory, we shall discuss a method of partial analysis. It is basically a mathematical technique which we shall develop or elaborate in our discussions today. But this method has some special characteristics. The most important one is this: the angular momentum of the interactive particle will come into play in defining the scattering parameters like scattering amplitude, cross section, etc. And another most implication of this method is the introduction of phase shift that we expect to occur in the scattered wave as a consequence of the interaction of incoming projectile with the scatter. So, what I like to say, this method will be elaborately discussed before you. We shall discuss in 4 parts: part 1, part 2, part 3 and part 4. So details can be written in 4 parts. In part 1, we shall discuss about the basic approach and the boundary condition. The basic approach and boundary condition. In part 2, we shall discuss about the derivatives of scattering parameters. Derivation of scattering parameters. And optical theorem. Derivation of scattering parameters and optical theorem. In part 3, we shall discuss about impact parameter. impact parameter and impact parameter and construction of partial wave zones. Impact parameter and construction of partial wave zones. In part 4, the last part, we shall talk about the convergence of partial waves and convergence of partial wave series and sign of phase shift. So in these 4 parts we shall discuss, and naturally we will go over the subject part by part, one after another. The basic approach and boundary condition. In this part, the students should keep in mind that the basis of this method stands on the representation of incident wave, scattered wave, and total wave function as a series expansion in terms of Legendre polynomial. So, the basis of this method stands on the representation of incident, scattered, as well as the total wave function as a series expansion in terms of Legendre polynomial. In developing this method of partial wave analysis, we must confine our attention to the collision of elastic type. So we shall consider only the elastic type of collision. Now let us write the features. The features of this method Let us write all the features one by one. Firstly, this method of partial wave analysis is an approximation method. So it is an approximation method. Which is valid only for spherically symmetric potential, that is V of R. Second feature is that the scattering parameters will be represented. Scattering parameters will be represented in terms of the angular momentum of the interacting particle. The third feature of this method is that the total phenomena can be viewed in parts in terms of different values of A. That means the total scattering phenomena can be viewed from a theoretician's point of view, that in parts in terms of different values of L. Next, point 4. The main implication of this method, is the introduction of phase shift. Which will be suffered by the incident beam as a result of scattering or interaction with the potential. Our next point is the point 5. We have told you that elastic type interaction. Secondly, interaction between or among the spinless particle. Spinless consideration. We have told you that the interaction potential that we would like to consider here is spherically symmetric. And if we consider z direction as incident direction of projectile, the Lz, that is m, is 0, and this will continue to remain 0. It will continue to remain as 0 throughout the interaction. Why is this so? Now, because of the spherical symmetry, due to V of R, central type. That's why. I mean, the total psi can be expressed as the sum over L, AL, RL, and your PL cos theta. Where L is the angular momentum and A is your arbitrary constant. L is an arbitrary normalization constant. Now, if we can represent the total function in this way, then the corresponding Schrodinger equation is relevant part. What is it? 1 over R square del R of minus L into L plus 1 by R square plus K square minus twice m by h cut square V of R RL R is the 0. Now, the radial wave solution RL in general is the combination of two functions. One is the spherical Bessel function and Neumann function. So, in general, RLR can be written as L JLKR plus, so it is BL eta LKR. This JLKR is a spherical Bessel function and eta is a Neumann function. So this JL is your spherical Bessel function. And this eta is known as Neumann function. Now question arises whether this general form is acceptable or not because of the boundary condition. Whether this general form is acceptable totally or not. So now we try to discuss about boundary conditions. So it is a boundary condition. Specifically, with reference to these two functions, we confine our attention to the boundary condition in such a way, firstly, that the wave function must be continuous, finite, elsewhere. A wave function must be finite elsewhere, including the origin, including the origin point are equal to 0. This is one point, the first point, say. The second one, at large R, that of large R, V of R, the potential must go to 0. Now let us see. The two functions graphically. It is your spherical Bessel function, that is JLKR, so it is the KR as argument, so it is 0.5, it is 1.0, this will be the another J. In this way, we can draw our function JLKR. Now, this is your J0 corresponding to L value 0. This is your J1 corresponding to L value 1, corresponding to L value 2, this is J2. Now, also let us draw the Newman function likewise. So it is the argument x, it is beta x. Now we are going to draw point 5, 1.0, for Neumann function, it is found that it looks like of this shape. If we like to draw the eta with respect to different L value, so it is eta 0 for eta 1, or eta 2, this will be of this type. Roughly I have drawn it, so just to show have the idea about the shape. Eta 1, eta 2. Now, I tell you to say that which one will be acceptable. Now, look at these two pictures, diagram. For this JLKR, you see the condition 1 is satisfied. That is, the function is finite everywhere, including the point 0, the origin. Here, for Neumann function, we see the function is discontinuous. So, our choice of acceptable solution would naturally become this spherical Bessel function. So, the choice of acceptable solution is eta LR as L JLKR. Okay? We can say that asymptotically what happens let us have an idea. Now, from the knowledge of our mathematical physics, and in that classes we all know the spherical Bessel function can be written in many forms, one of which that is very important for our case is that the asymptotic form of JLKR can be written as sine KR minus L pi by 2 divided by KR. So it is JLKR at large r. Free particle. So it represents free particle. Okay? So the asymptotic form of JLKR that we have written here in terms of the sign function, which represents the free particle. Now, as we are discussing about the scattering phenomena, so it is quite natural to expect that the scattered wave must be such that it must contain some information about the interaction potential. I mean, the scattered wave must be differing from the incident wave at least by one such factor that it suffers some interaction. So, now our task is to represent the function to get the information of potential or the effect of potential. So what I'd like to say that to incorporate the effect of the potential, we can add a phase term say delta L in the argument of the function of JLKR. Actually, the introduction of this delta L, the delta L can be introduced if the potential falls off very rapidly, or very faster than 1 over r. So it's a point to keep in mind that for those cases where the potential falls off very faster than 1 over r, we can introduce the phase factor delta L without losing the generality of the solution. So, without any loss of generality, we can write JLKR at large R as sine kr minus L phi by 2 as it was for free particle plus an extra term delta L whole divided by kr. So this expression for sine function gives you the information or carries some information about the potential because of the presence of this delta L. Actually, whenever a wave crosses a potential, a phase change will occur. It's a natural event. And so, this is our proposal, or this is the reason behind which, or depending upon which, we can write this expression. Okay? So let us say this expression as equation number, it would be, say 5. Now, let us try to rewrite this expression in a convenient form in order to go into the details of this partial wave analysis method. So let us write this expression in another suitable form. This is equal to I kr minus L pi by 2 plus delta L minus e to the power minus I k dot r minus L pi by 2 plus delta L whole divided by twice I kr. So we are writing about your JL kr. Now take common of e to the power I delta, e to the power minus I del L, and with a minus sign. If we take it common, then it will be e to the power minus I k dot r minus L pi by 2 minus e to the power twice I del L into e to the power plus I k dot r minus L pi by 2 whole divided by twice I k r. We have just taken common e to the power minus I delta from this part, and then it turns into this set. Now this e to the power twice I delta can be written also in a different form. Okay, before going to that, now also we need to write in this way that we all know e to the power I plus minus L pi by 2 means this. So introducing this, we can write it again in the form minus I to the power L from this part, because of e to the power plus L pi by 2 means only plus I to the power L. A minus sign was initially there. E to the power minus I del L by twice I kr as it was, no change. Only the factor I to the power L is taken out. So the remaining terms are e to the power minus I k dot r minus, let us rewrite this term as SL into minus 1 to the power L, because of this factor, as we have taken common, into e to the power I k r. Now, proceeding in this way, of course we can write it here that where SL to the power twice I del L, twice I del L is called the S matrix element. It is known as S matrix. S matrix. It is a S matrix such that SL star SL gives you unit. Is it now clear to you? I have taken I to the power L as common. So there is one minus I to the power L. So it will be minus I to the power L, and as I is common, so it will becomes minus 1 to the power L. So this is the desired relation up till now, and let us call it as equation number 6. Now look at the point that if delta L equal to 0, what we will get? We immediately go over to our free particle solution. Free particle solution, and that has been given in equation 4. So what I like to say, that if I put delta L equal to 0 here, we will get the representation of JKR corresponding to a free particle. Also, you note that this delta L is called the nth order phase shift. It is called nth order phase shift. Delta L is known as nth order phase shift. Now another point, the point 1 was this. Next point, that this expression 6 is a combination of an incident wave and an outgoing wave. So the expression 6 expresses two parts, which expresses two parts. One is your incoming wave and the other one is outgoing. So we can say that expression 6 contain an incoming and an outgoing wave structure. Incoming and outgoing wave structure. Now let us rewrite the general asymptotic form of RL, the radial wave solution. So, the general asymptotic form of psi can be written as at large R sum over L runs from 0 to infinity, L sine kr minus L pi by 2 plus del L whole divided by kr into the Legendre polynomial PL cos theta. Now let us write this expression in full form of this as sum over L minus L I to the power L e to the power minus I del L whole divided by twice I k r, and then it will be to the power minus I k dot r minus 1 to the power L SL to the power plus I k dot r into PL cos theta. So we have just rewritten this expression by substituting sin kr in the form of exponential function. Now this term can be broken up in two parts just for our mathematical technique. Let us derive this in this way. Sum over L minus L I to the power L e to the power minus I del L by twice I k r into e to the power minus I k dot r minus 1 to the power L e to the power plus I k dot r PL cosine theta. This may be the first part, and then plus sum over L AL I to the power L e to the power minus I del L by twice I k r. It will remain as it is into SL minus 1 to the power plus I a dot r PL cos theta. Mark this equation as equation number 7. Of course, one thing is missing here. This should be minus 1 to the power L. I have missed to write it here. Okay. Now, this is the general side. I mean the total side. This has two components. Now again, let us write down the expression for incident plenary. The incident plane wave can be written as, can be expressed as e to the power ikz, as we have taken the incidence along z axis, e to the power ikz means e to the power I k r cos theta. Now this can be written in terms of the angular momentum eigenfunction. Already you know from your mathematical physics classes that this can be expressed or written as sum over L I to the power L twice L plus 1 JL KR and your PL cos theta, JL KR PL. If we now substitute the value of JL KR in terms of the exponential function, then it can be written as sum over L I to the power L minus I to the power L AL by twice IKR into to the power minus I K dot R minus of minus 1 to the power L to the power IK dot R. So this is the part of the JLKR, and the remaining one is the PL cos theta. This is the expression for okay. Now let us pass over to a new discussion. Of course, there is one thing extra. This AL should not be there, because JLKR doesn't contain AL. AL is associated with the total form of RL. That's why this AL should not be there. Now, look, these two expressions, one is the total psi, which has been written in terms of the angular momentum eigenfunction, and the incident wave, which is also written in the same style. So these two styles, as I told you before, that these are the basis of approach of this method. Unless you express both the incident and the scattered wave or the total psi in terms of this form, we cannot pass into this method of partial wave analysis. So now let us again come back to the demand of general theory. So by the demand of general theory, we expect that the total psi can be written as, or can have to be written as e to the power ikz plus f theta e to the power ikr ik dot r by r. This is what, say, expression number 9. Actually, we all are familiar with this last relation of the expression 9, because it is nothing but the general demand of our scattering theory. Now, we shall start to have the value of L, to identify the values of L and f theta. So let us do that. So from expression 7, 8 and 9. From equations 7, 8 and 9, one can identify that L e to the power minus I delta L is equal to I to the power L twice L plus 1. You look at this relation that if it is e to the power ikz, and if ikz is this much, comparing this with this relation, you see this is equivalent to this rest of the part. Only differences is that a to the power L, AL e to the power minus I del L must be equal to, can be equated to here as I to the power L twice L plus 1. In this relation, I have missed to write the twice L plus 1. Okay. So from this, I can get the normalization constant L as I to the power L twice L plus 1 e to the power I del L. Actually, this is the value of AL. Let it be marked by equation number 10. Now, once you get the value of AL by identifying the e to the power ikz and this thing, now we can also identify the value of f theta. Let us do that now.